Hi, I am Dr. Wasim Sheikh. In this video, we will talk about surface defects, which are also known as 2D imperfection in solids. So, let us begin. So, what are surface defects or 2D imperfections? So, surface or interfacial defects are boundaries that are formed, and normally they separate the two regions which are there in a crystal or in a solid. So basically, when we have two separate regions, these two regions can have a different crystallographic structure or they can have a different crystallographic orientation. So these types of defects basically includes grain boundary and stacking fault. So let us start with grain boundary. What are grain boundaries and how these grain boundaries are formed? So in an earlier video, we saw the solidification process and how solidification takes place. So during the process of solidification, we have seen that at different places these nuclei are starting to form and then they form grains. So each and every grain is formed in a polycrystalline material, and when the material completely solidifies, these individual grain they come together and then they form a grain boundary. So this grain boundary is nothing but it is a type of defect. So ideally we don't want any grain boundaries in the material, but inherently in the process, because of the solidification, we get these types of grain boundary which are there in the material, and it is nothing but a mismatch or an atomic mismatch which is there. And these grain boundaries which are there, these have lot of energy which is concentrated in between them, and basically that is not desirable. So here we see an image which shows that we have different grain. The grains are oriented in different fashion. They have the same structure but they are oriented in different fashion, and then we can see that there is an angle of mismatch or the angle of orientation which is there, and it can be of two types. So it can have a high angle grain boundary or it can have a low angle grain boundary. So we'll see what is the differentiation between high angle and low angle grain boundary. But here let us see that this is an image which shows that in between we have a grain on the top, and on the bottom, at the bottom we have grains, and then in between we have the grain boundary, and that is the misalignment, and the structure is same but the orientation is different. So each grain or crystal tends to have different crystallographic orientation, as we have seen earlier. Atoms are bonded less regularly at the grain boundary and they tend to have a higher interfacial energy, and because of that we can have high angle grain boundary or we can have a low angle grain boundary, but interfacial energy is very higher in high angle grain boundary and interfacial energy is lower at a low angle grain boundary. So thus these grain boundary are very chemically reactive than the normal grain. So it is more chemically reactive at the grain boundary. So the material is more reactive at the grain boundary, at normally not along the grain but along the grain boundary. So here this image again we can see that two grains are there. There is a mismatch which is happening. The orientation of the grain is different, and then because of that we are forming a low angle grain boundary. So how we can differentiate between a high angle and a low angle grain boundary? Generally when the misorientation angle is less than 15 degree, then we call that grain boundary as a low angle grain boundary, and when that misalignment angle or angle of misalignment is more than 15 degree, we call that as a high angle grain boundary. So small or low angle grain boundary formed when edge dislocation aligned to form an array known as a tilt boundary. So thus angle of misorientation is typically less than 15 degrees. This is an image which shows an high angle grain boundary. Again here you can see two grains are there. The orientation or the misalignment angle of the grains are much higher than 15 degree. That is why we call them as high angle grain boundary. So generally GB is the notation which we can give for grain boundary. High angle grain boundary, most of the grains they are having high angle grain boundary. High angle grain boundaries are formed when the angle of misorientation, or theta we generally call that, is greater than 15 degrees. So now let us come to the second one, or the second two-dimensional imperfection other than grain boundary, is the stacking fault. So in material, let us take an example of FCC. In an FCC metal, the general stacking of the plane is in terms of ABC packing sequence is there. So after every plane, every three plane, the stacking of the plane repeats. So if we have ABC, the stacking is ABC, and that is in terms of the plane. When we see an FCC crystal structure, which is coming up in the next slide, we'll see what is exactly that stacking. But if any of these plane is missing, then we have a stacking fault. So here as an example, we see ABC, then BC. So A is missing. So plane A is missing. So that is creating a stacking fault or a stacking two-dimensional imperfection in the material, and that is nothing but a imperfection in the material of two dimension. That is called as a stacking fault. So the interfacial defect that exists within the FCC stacking sequence is a stacking fault which occurs between the two lines. So basically one line of atom or one plane is missing. So here we can see that the planes are there ABC. This is the close pack stacking sequence of FCC structure if we see from one of the corners. So if you look from this corner of the crystal structure, each and every plane is color coded, and the earlier image which you saw was the plane was stacking on top of each other, but here it's a three-dimensional image, and then you can see the stacking sequence. So a corner has been removed basically from this image to show the relation between the stacking of close packed plane of atoms and the FCC crystal structure. The heavy triangle outline is the 111 plane. So in an earlier video we have discussed that in FCC plane, 111 plane is the closely packed plane, it is highly packed plane, and now when we look from the corner, you can exactly see this plane as in a triangle, and all these planes are stacked on top of each other. When we look from the corner, if one of these planes are missing, it is a stacking fault. Again, let us look at this image. This is an FCC and an HCP crystal structure, and then we are looking in terms of the close packed plane, and again the sequence is there ABC, and if one of the plane or one of the stacking plane is missing, then we have a stacking fault. So here both the images give a comparison. Again in HCP we have AB stacking. So in FCC we have ABC stacking. In an HCP hexagonal close pack we have AB. Again in this AB sequence, any plane is missing, then there is a stacking fault. Okay, so now in this video we have discussed about surface defects, we have talked about grain boundary, we have discussed about high angle grain boundary and low angle grain boundary. So in low angle grain boundary, the angle of misorientation is less than 15 degree. In an high angle grain boundary, the angle of misorientation is greater than 15 degree. Grain boundaries are formed during the solidification process. You can't avoid the formation of grain boundary in a polycrystalline material. Grain boundaries have a lot of energy which is concentrated in them, and then they are highly reactive, and we have grain boundaries. So now the next one is stacking fault. We saw that in each and every crystal structure there is a stacking sequence like ABC in an FCC, AB in an HCP, and if any of these plane is missing, then we have a stacking fault. So I hope you understood about the two-dimensional defects, and if you like the video, please give it a thumbs up, and if you like my channel, if you like my video, please subscribe to my channel. So thanks a lot, all the best.